Delaware Tech, Chemistry 110, Chemical Quantities and Reactions Continued, Stoichiometry Calculations. So we've already talked about what stoichiometry is and the concept of how to build a map of how to calculate things in stoichiometry, but we haven't done an actual calculation. So this module will go over a number of examples using simple stoichiometry to calculate amounts of reactants and products in a chemical reaction. And in this particular reaction, it says how many grams of ammonia, NH3, will be produced if 10.0 grams of hydrogen gas, H2, are reacted with an excess of nitrogen gas, N2. And it's important to mention that it's an excess only to tell you that we're not going to run out of nitrogen during the reaction. So you can just worry only about the hydrogen gas being used to make ammonia. And this particular reaction, N2 plus 3H2, produced 2 ammonia. This is called the Haber-Bosch process. It was invented between 1900 and 1910 by 2 German chemists by the name of Fritz Haber and Karl Bosch. And I show this reaction, and you often see this in chemistry textbooks, and they kind of gloss over this reaction. It's two gases reacting to form a third gas. And you might think, okay, so what? Well, this reaction is actually one of the most important chemical reactions in the history of humankind. This reaction, invented by these 2 brilliant scientists, allows us to produce ammonia. Well, why is that important? Well, ammonia is the starting material for making fertilizer. It's also the starting material for making a lot of other things, including explosives that were later used in World War I. But fertilizer is the most important use, and it's still used today. This chemical reaction is over 100 years old, and it is still being used today. And in fact, the nitrogen that's in the ammonia product of this reaction is so important because it is the reason why we're able to have farms all over the world producing enough food to supply the population. Without this process, human population would have never exploded to the amount that it is. And in fact, if you look at population graphs over time, you will see that the population of the Earth exploded within 20 years of the production of this chemical reaction, the first reaction. And in fact, it's been estimated that 50% of all the nitrogen in your body is actually from the ammonia that was manufactured in some factory using the Haber-Bosch process. So it is enormously important for producing the world's agriculture. Anyway, so we have this reaction. It's a very interesting reaction. We're given a number of grams of hydrogen. We're asked for how many grams of ammonia. Okay, how do we proceed? Well, it's a stoichiometry problem, so we always have to start with a balanced equation. And I've already balanced it for you. It's 1 nitrogen plus 3 hydrogens make 2 ammonias, a 1 to 3 to 2 ratio of the reactants and products, and this is fixed. For every 1 mole of nitrogen, I need 3 moles of hydrogen. For every 3 moles of hydrogen, I will get 2 moles of ammonia. For every 2 moles of ammonia, I need 1 mole of nitrogen and 3 moles of hydrogen to produce it. Those are fixed ratios from the balanced equation. So this will give me any pair, the ratio of any 2 of these. It doesn't matter which 2. So I can give you a reactant, I can give you a product, I can ask for anything else from this. And in this particular problem, I'm giving you the amount of hydrogen gas in grams, not moles, in grams. So you know for every 3 moles of hydrogen, you'll get 2 moles of ammonia. But first you have, so this allows you to convert moles of one thing to moles of anything else. But you have grams in this problem. And whenever you see grams involved in a stoichiometry problem, you're going to need the molar mass for every substance that either starts with grams or will end with grams. Because you need the molar mass to convert grams to moles and then moles to grams for the other substance. So it's important to get those molar masses. And that allows you to do these conversions. Now you have all the things you need. Once you have the molar masses, once you have the balanced equation, now you can build your mathematical equation starting with the thing you have. What is the thing you have? 10 grams of hydrogen gas, H2. Start with that. Well, what do you know how to convert grams of hydrogen to? Well, the only thing you know how to convert grams of hydrogen to are moles of hydrogen. And you use the molar mass to do that. The molar mass of hydrogen is 2 times the molar mass of a hydrogen atom, which would be 2.0158 grams per mole, or 2.0158 grams of hydrogen is equivalent to 1 mole of hydrogen. Remember, conversion factors are just disguised versions of 1. So the top must be the same thing as the bottom in one way or another, or at least equivalent to in some fashion. And so we're literally dividing our original grams of hydrogen, 10 grams, by the molar mass. And we do that because we want grams on the bottom, we want moles on the top. We are converting grams of hydrogen to moles of hydrogen. And you'll notice I've written hydrogen. I haven't written just grams. I haven't written just moles. I've written moles of hydrogen. I've written grams of hydrogen. And that's because grams of hydrogen are not the same thing as grams of ammonia. And moles of hydrogen are not the same thing as moles of ammonia. So the whole unit here is moles of hydrogen, or moles of ammonia, or grams of hydrogen, or grams of ammonia. You need both parts of to make a whole unit. Moles of hydrogen cannot cancel moles of ammonia. Grams of hydrogen cannot cancel grams of ammonia. Those are 2 different things. So you need to be careful with your units. Now, if we just stopped here, we would cancel grams and we'd end up with 4.96 moles of hydrogen. But we're not asked for moles of hydrogen. If we wanted moles of hydrogen, we could stop here and that would be the end of it. But we don't want that. Remember, we're trying to get to grams of nitrogen. Grams of ammonia. So we have the moles of hydrogen. We can use the balanced equation to convert moles of hydrogen to moles of ammonia. We know the ratio of moles of hydrogen to moles of ammonia is 3:2. Whenever you build your conversion factor, always put your units in first. Moles of hydrogen on the bottom, moles of ammonia on the top, and then you populate it with the number. Just like when we used in the red here, the molar mass conversion factor, we want grams of hydrogen on the bottom and moles of hydrogen on the top. And this, having these in this way, written this way, allows us to cancel 2 more units, moles of hydrogen. And if we stopped here, we would get 3.31 moles of ammonia. But we're not looking for moles of ammonia, we're asked for grams of ammonia. So we do 1 more conversion. And we have grams of ammonia, we know how to convert that to moles, we have moles of ammonia, we know how to convert it to grams of ammonia. We multiply it times the molar mass. Don't just multiply by the molar mass, build your conversion factor. You know you want moles of ammonia on the bottom, you know you want grams of ammonia on the top, you know that 1 mole of ammonia is equal to 17.0305 grams of ammonia. How do you know that? Because you added up the molar masses of nitrogen atoms and 3 hydrogen atoms. Each hydrogen is about 1, each nitrogen is about 14. 14 plus 3 ones is about 17, and that makes sense. So make sure your molar masses make sense. And now when you multiply this out, you'll actually be able to cancel the last pair of units, moles of ammonia with moles of ammonia, and the only unit left here is grams of ammonia. And you see that in the end, you'll get 56.3 grams of ammonia. Now, does that make sense? You started with only 10 grams of hydrogen, but you ended up with 56.3 grams of ammonia. Well, look at the equation. You see that ammonia is composed of, for every 3 moles of hydrogen, which doesn't weigh much. It's only 2 grams per mole, roughly. You'll get 2 moles of ammonia. That's less moles, but each ammonia molecule, each mole of ammonia has a lot more mass than each mole of hydrogen. So we do end up with a lot more grams, a lot more mass of ammonia, and that makes sense. Here's another example. 10.1 grams of iron are added to a solution of copper 2 sulfate. How many grams of solid copper would be formed? Okay, you're going from iron and copper sulfate to solid copper metal. Well, First, we have to determine the formula of each reactant. Well, iron is given to you. It's just Fe. It's a single atom. But you also have copper sulfate, and you have to use your rules of nomenclature to remember what copper 2 sulfate is. Copper 1 sulfate would have 2 coppers in it. You're going to use crisscross simplify to get your formula. And you have a reaction here with elemental iron and a compound of copper sulfate. This suggests that your reaction type is a single replacement. Now, in this particular example, iron, remember, can form +2 or +3. I'm going to tell you that in this case it will form +3. It's a bit more stable as an ion than +2, and in this particular reaction we'll get +3. So how do you determine your products? Well, you know one of the products is copper, so you just write Cu. That's easy. But the other one will be, since it's a single replacement, you are replacing the copper with iron. So you swap those two, and now the iron will be with the sulfate. But the iron is +3, the sulfate is -2, and that means you need to use crisscross simplify to determine the formula of your iron 3 sulfate product. And that's Fe2, parentheses, SO4, close parentheses, 3. In other words, 2 irons and 3 sulfates are in this particular formula unit. So now you have the right formulas of all the components, of all your reactants, of all your products. Now you need to balance the equation. You already know the rules of balancing. I'm not going to go over those again. Let's assume you get the balancing, and you know from the balanced equation that the ratio of all your reactants and products are 2 to 3 to 1 to 3. We don't write the 1, but remember it is a 1. You can write the 1, that's not a problem if you do, but you don't need to write the 1. So you know that for every 2 irons, you'll get 3 coppers. For every 3 copper sulfates, you'll get 1 iron sulfate. 3 copper 2 sulfates, you'll get 1 iron 3 sulfate. For every 2 irons, you'll get 1 iron 3 sulfate. So you know the ratio of any 2 of these right away. You now have a whole set of conversion factors for that. But this is a problem that has grams in it, and anytime you're given grams and anytime you're asked for grams, you're going to need a molar mass, which has a units of grams per mole. And so you're given grams of iron, you're going to need the molar mass of iron. Well, that's easy. You just look it up on the periodic table, because the molar mass number is the same as the atomic mass number. It just has different units, grams per mole. And same, you're asked for grams of copper. So that one you can just look up as well. And I put the other 2 in here. You can practice those to see if you come up with the same totals for iron 3 sulfate and copper 2 sulfate. I've written them in, but you don't need them for this particular problem. You might need them for another follow-up question. So always keep in mind you might need another molar mass later on. So now we have all our conversion factors. We're able to build our equation. So now we create our stoichiometry map, our problem map. What is going to go to what, to what, to what, to go from grams of iron to eventually grams of copper? Well, we can go from grams of iron to moles of iron using its molar mass, and we can go from moles of copper to grams of copper using its molar mass, and in the middle of this, we can go from moles of iron to moles of copper, because we know that for every 2 moles of iron, we'll make 3 moles of copper, and that's our middle conversion factor. So we build our formula now. Start with what you have. 10.1 grams of iron. Convert it one at a time. Or you can do it all in one shot. It doesn't really matter. I like to put them all in and then just do the multiplication. If I'm asked for any intermediate thing, I can stop and calculate that. But this is asking for grams of copper. So first I'm going to use the molar mass. I'm going to put grams of iron on the bottom, moles of iron on the top, and then put the right numbers in. Now, if I stopped here, I'd have moles of iron. But I don't want moles of iron. I want to keep going. I can convert moles of iron to moles of copper because I know I will have a certain number of moles of copper per moles of iron. Build your conversion factor first. Put your line in the middle. Put your unit on the top, your unit on the bottom. Remember, the one on the bottom is being canceled. The one on the top is being created. So you want moles of iron on the bottom, moles of copper on the top, and then put the numbers in. Don't put any numbers in a conversion factor until you put the units in. You're going to make a mistake otherwise. I have made mistakes plenty of times because I rushed my conversion factors. Well, if I stopped here, I would get moles of copper. Everything else would be canceled. But I want to convert my moles of copper to grams of copper. I use the molar mass of copper. So I want moles of copper on the bottom. Well, for every 1 mole of copper, I will have 63.546 grams of copper, because the molar mass is 63.546 grams of copper per 1 mole of copper. It's just another way of saying 63.546 grams per mole for copper. Now we can cancel everything that needs to be canceled. Grams of iron, moles of iron and moles of iron, moles of copper and moles of copper. And this is why it's so important to include the names of the compounds with your unit. The unit is not moles. The unit is moles of iron or moles of copper. The unit is not grams. It's grams of iron or grams of copper. And only the identical units can be canceled here. And in the end, the only unit we have left is grams of copper. We get an answer, and now we have to remember, round it. We started with a 10.1 grams. That's 3 significant digits. And all our conversion factors have at least that many. Our molar masses each have 5 significant digits, 55.845 and 63.546. And something to consider here are 3 moles of copper to 2 moles of iron. That's an exact ratio. It's exactly 3 moles of copper for every exactly 2 moles of iron we start with. So 3 over 2 actually has infinite sig figs. Any balanced equation coefficient ratio will always have infinite sig figs because it's exactly that ratio. And therefore, you never have to worry about it. All of my conversion factors have either 5 or infinite sig figs. Those are much bigger numbers than 3 sig figs. So if I start with 3 sig figs, I'm probably going to end with 3 sig figs. So I round my final answer to 3 sig figs, or 17.2 grams of copper. And that makes sense. We're going to get 3 moles of copper for every mole of iron, and copper weighs a little bit more than iron. 63.5 versus 55.8 or so grams per mole. So we expect to have more mass of copper in the end. Here's a practice problem for you. Given the following reaction, how many grams of aluminum oxide, Al2O3, will be produced if 23.65 grams of aluminum metal, that's just Al, are reacted with an excess of oxygen gas? I'm telling you there's an excess so you don't have to worry about the oxygen. You just consider that all of the aluminum will react because you've got tons of oxygen to react it with. So you're just worried about how much product you can get from this much aluminum. So what are you going to need? Well, you're going to need what you always need. The balanced equation. Well, I've given you the balanced equation, so that's easy. And you're going to need any molar masses that allow you to go from grams to moles or moles to grams. Well, you're given grams of aluminum. You're asked for moles of aluminum oxide, so you're going to need 2 molar masses in the process. And I've gone and calculated these for you, but make sure you get the same answers. The molar mass for the aluminum, this might be slightly different now. They're always updating aluminum's value, but this is right from the periodic table. Oxygen is just 2 oxygen atoms, so you just multiply the molar mass of 1 oxygen atom times 2. And aluminum oxide, you have to add up 2 aluminums and 3 oxygens to get its molar mass in grams per mole. We have the coefficients, so that gives us those ratios. So we have everything we need to build our equation now. And you're going to start with the thing you have. And you can pause right here and see if you can build the same coefficients and conversion factors to get the answer. Okay, so you have grams of aluminum. What are you going to convert it to? Moles of aluminum. You're going to convert moles of aluminum, which you can calculate. You can stop there and calculate directly, or you can keep going, just add more conversion factors. You can convert moles of aluminum to moles of aluminum oxide, because you know you get 2 moles of aluminum oxide for every 4 moles of aluminum. Don't simplify your ratio from 2 to 4 to 1 to 2, because it'll confuse things later. Keep the numbers the way they are. Believe me, simplifying will not simplify your math later on. So just keep it 2 moles of aluminum oxide for every 4 moles of aluminum. And if you stopped here, we would get that we had 0.4383 moles of aluminum oxide, but of course we want grams of aluminum oxide, so we multiply that by grams per mole of the aluminum oxide, and we end up with our final product of 44.69 grams of aluminum oxide. I've already rounded it to 4 significant figures. Why? Well, our 2 molar masses have lots of sig figs in them, and our balanced equation coefficients in the middle have infinite sig figs. So if we start with 4, we're going to probably end with 4 sig figs. 44.69 grams of aluminum oxide. So here's a follow-up question on the same problem. Given the above reaction, how many grams of oxygen gas, so this is why we have the molar mass of oxygen gas, are required to produce 100 grams of aluminum oxide? So now we're given the product, and we're asked for how much of a reactant we need. It doesn't really matter which way we're going. You're going from one substance in the equation to another. It doesn't matter if it's reactant to product, product to reactant, product to product, reactant to reactant. If you have one amount of one thing, you can always calculate the amount of anything else in the equation. We always start with what we have, 100 grams of aluminum oxide. We convert that to moles of aluminum oxide in red. We convert that to moles of oxygen in green. We convert that to grams of oxygen in light blue, and we end up with 47.1 grams of oxygen are required to make 100 grams of our aluminum oxide product. Here's another example. Given the following reaction, if 50.9 grams of pentane, C5H12, are combusted, what does combusted mean? It means reacted with oxygen to produce CO2 and water. With an excess of oxygen gas. That's so you don't worry about the oxygen gas. How many grams of CO2 will you produce? Well, you're given a certain thing. You're already given the balanced equation. You need the molar masses of pentane. You're going to need the molar mass of carbon dioxide. I've included the others just in case there are follow-up questions, but you don't need to calculate them if you're not going to convert anything. You only need the one for pentane and the one for CO2. And now we have everything we need to build our equation. I'll pause here, see if you can figure it out. Okay, so we start with the grams of pentane, we turn it into moles of pentane, we turn moles of pentane into moles of CO2, we turn moles of CO2 into grams of CO2. Every arrow is a conversion factor. We start with what we have, we convert it to moles of pentane, we convert moles of pentane to moles of CO2. We convert our moles of CO2 to grams of CO2. Everything cancels except grams of CO2 in the end, and we end up with 155.24 grams of CO2, which we round to 3 significant digits, 155 grams of CO2. Follow-up question. Given the above reaction, how many grams of pentane are required to completely react with 67.3 grams of oxygen? Well, you do the same thing, but now you're starting with oxygen. I'll pause here and see if you can do the whole thing yourself. Okay? And here it is. You're taking oxygen in grams, divided by its molar mass to get moles, turn moles of oxygen to moles of pentane in green, turned moles of pentane in the light blue to grams of pentane in the final answer. 19.0 grams of pentane are needed to burn with 67.3 grams of oxygen. So shown on this slide are some follow-up problems that use the exact same chemical reaction, that is the combustion of pentane. So we're going to need our molar masses again, and I'll just put those in here so you have them for reference and you have your balanced equation. But you'll notice in these particular questions, you're not always going from grams to grams. You are in the last example, but sometimes you're asked to stop at moles, sometimes you're starting at moles. And that actually makes things much easier. You get to skip a step if somebody gives you moles of something. You get to stop early if somebody asks for moles instead of grams. So that's actually, it might seem a little confusing, but it actually makes it much easier. Let's look at the first one. How many grams of pentane are needed to produce 14.5 moles of water? Well, what's our map here? Well, we're starting with 14.5 moles of water. Well, we've already got moles. So we can go directly to moles of water to moles of anything else using the balanced equation. We want moles of pentane. And then once we have moles of pentane, we can easily convert it to grams of pentane. So I can pause here, see if you can put the equation together. Okay, and here it is. 14.5 moles of oxygen. We use the 1 mole of pentane to 8 moles of oxygen ratio from the balanced equation to turn moles of oxygen into moles of pentane, and then we multiply it by its molar mass to get 131 grams of pentane are produced. Second question, how many moles of CO2 will be produced from 43.1 grams of oxygen gas? All right, I'll pause here. Okay, let's see how you did. All right, we're starting with 43.1 grams of oxygen, and we're asked for moles of carbon dioxide, so we get to stop early. We're going from grams of oxygen to moles of oxygen to moles of CO2, and that allows us to only use 2 conversion factors. We don't have to go to grams of CO2, so we stop at 0.842 moles of CO2. And the last example is another full grams to grams question. How many grams of pentane will react with 895 grams of oxygen gas? Well, I'll stop here for a second. You can pause it. Okay, you're starting with what you have, 895 grams of oxygen. You need to turn grams of oxygen to moles of oxygen to moles of pentane to grams of pentane. And we do that using the conversion factors that you already know, 2 molar masses and 1 in the middle from the balanced equation. And we get 254 grams of pentane will react with 895 grams of oxygen gas. There's another set, and I'll let you work on these yourself. This one's an equation that looks more complex, and it's already balanced for you, so you don't have to worry about that. It says the U.S. Space Shuttle boosters use the following reaction. And this is actually one of the reactions that's really used to launch rockets in space. This is 10 aluminums plus 6 ammonium perchlorates. These are very reactive molecules. Produce 4 aluminum oxides plus 2 aluminum chlorides plus 3 nitrogen gases plus 12 waters. This is a very heat-producing reaction, what we call exothermic. You'll learn about that later. An enormous amount of energy. And you have 3 different problems, and they're all going from grams to grams. Grams of aluminum, you're asked for grams of aluminum in the first one, but you're given grams of ammonium perchlorate. In the second one, you're asked for grams of water, and you're given grams of ammonium perchlorate. And the last one, you're asked for grams of aluminum chloride, and you're given grams of ammonium perchlorate. So you see grams of ammonium perchlorate in all of these questions, so you're going to need the molar mass of ammonium perchlorate. You see grams of aluminum in the first one, grams of water in the second, grams of aluminum chloride in the third, so you're going to need all of those molar masses as well. Anytime you see grams, whether it's given to you or asked of you, you're going to need a molar mass. So I'll pause here and see if you can work out the entire problems start to finish, and I'll wait. Okay. All right, I'm going to start back up again, and let's go over the first one. Here are your molar masses before we start. How many grams of aluminum must be used to react with 652 grams of ammonium perchlorate? We're going to go from grams of ammonium chlorate to moles of ammonium chlorate, moles of ammonium chlorate to moles of aluminum to grams of aluminum. And there are 4 conversion factors with the units in the right place. We end up with 250 grams of aluminum. Next one, how many grams of water produced from 652 grams of ammonium perchlorate. It's the same number of grams in each case. We want to know how many of the other things. So we're going to start with the same thing. I'll pause here, see if you can build the equation. Okay, here we go. Here's your map, and here's your equation. We end up with 200 grams of water will be produced in this reaction. And the last one, we're asked for ammonium chloride. I'll pause here. Okay, and let's see how you did. And we end up needing, producing 247 grams of aluminum chloride in the process. So here are 3 problems for you to practice on your own. These are 3 good examples of the kinds of problems you're going to get, though you'll have to balance your own equations and you'll have to determine your own molar masses to get all those different conversion factors. So, finally, let's talk about stoichiometry and how it can be used to confirm the law of conservation of mass, also known as the conservation of matter, more properly known as the conservation of mass energy, because we know that mass and energy really are equivalent versions of the same stuff in the universe. But we're just going to keep it to mass for now. And we have our old hydrogen and oxygen burning to produce water reaction. This is a combination reaction. It's technically also combustion, but since it's not a carbon compound, you in this class will not be referring to this as a combustion reaction, though chemists do refer to it that way. How many grams are in 2 moles of hydrogen gas used in this reaction? So we're going to think of this reaction as if it's actually 2 moles of hydrogen plus 1 mole of oxygen produce 2 moles of hydrogen, of 2 moles of H2O, of water. So how many grams are in 2 moles of H2O? Well, we know 1 mole has 2.01588 grams per 1 mole of hydrogen gas. 2 moles is just double that. And we could use our conversion factors to figure that out. It's a little more than 4 grams of hydrogen. How many grams are in 1 mole of oxygen gas, the other reactant in this problem? Well, 1 mole of oxygen gas has a molar mass of oxygen gas has a molar mass of 31.9988 grams per mole. We have only 1 mole, so it's the same number of grams. And how many grams are there total if we add these 2 together in our reaction? Well, that's 36.0306 grams of reactants. That's how many grams we start with. Well, what are our products? Our products are 2 moles of water. How many grams are in 2 moles of water? Well, 1 mole of water is 18.0153 grams. That's how many grams per mole for water. It's up at the top in red. We have 2 moles. We multiply that times 2, and we get 36.0306 grams of products. So the number of grams of reactants is exactly equal to the number of grams of products, assuming the reaction goes to completion, that all of the hydrogen and all of the oxygen reacts to form water, and that there's no remaining hydrogen and oxygen gas left after the reaction. And this reaction goes to completion very easily. It's a very hot reaction. It produces quite a beautiful flame, as a matter of fact, when you burn hydrogen gas. And you see that the mass is conserved. It's exactly the same number of grams before and after. And we'll stop here.